In this video, we're going to talk about function notation and evaluating functions. When we write algebraic representations of functions, we will always write them with the y variable isolated on one side. For example, here I've written an equation in function form with the y isolated on the left side of the equation. Y equals 2x plus 5 is an example of a linear function. Here I've written an equation in function form with the y isolated on the left side of the equation as well. Y equals x squared minus 3x plus 7 is an example of a quadratic function. But functions have a special notation. Rather than writing y equals, we'll write f of x equals. And as you can see, f of x and y are the same thing. F of x is just a fancy way to say y. Using function notation also gives us a pretty slick way to write a lot of information in a short amount of space. For example, you see here that the letter f gives us the name of our function. We can really use any letter we want to name a function, but f, g, and h are the most popular letters. You can also see that using function notation gives us a way to identify our input and our outputs for a function. Now, this notation does not mean f times x equals y. This means f of x equals y. We call the x, the input, the independent variable, and y, the dependent variable. When we use function notation, the independent variable, or the input, plays the role of a placeholder. For example, in the function f of x equals x squared plus 5x minus 3, that function can be viewed as f of blank equals blank squared plus 5 times blank minus 3. To evaluate a function at a number, we simply substitute the number for the placeholder, or substitute the number for the blank. When we evaluate a function, we're finding the y-coordinate of the ordered pairs. Another way to say this is that we are finding the height of a graph for a certain value of x. Let's evaluate this function when x equals 3. Here we have the function f of x is equal to 2x squared minus 8x plus 12. Now just remember that the x's, the inputs, are just placeholders for my value. In other words, everywhere I see an x in this function, I'm going to place the value of 3 because I want to evaluate the function when x is equal to 3. When I substitute x for 3, I get f of 3 equals 2 times 3 squared minus 8 times 3 plus 12. Now all we have to do is use the order of operations to find the value of f of 3. So we have 2 times 9 minus 24 plus 12. 2 times 9 gives us 18. So we have 18 minus 24 plus 12. And 18 minus 24 plus 12 gives us 6. So f of 3 equals 6. Another way to say this is that the function f, when evaluated at 3, gives us a height of 6. F of 3 equals 6 corresponds to an ordered pair that would be on the graph of this function 2x squared minus 8x plus 12. That would be the point 3, 6. So we should expect to see the point 3, 6 on the graph of this function. And remember what I said earlier. When we evaluate a function, we're finding the height of a function at a certain x value. Well, here the height of our function is 6. That's the y value. When x is equal to 3. That's our x value. Find g of 1/2 if g of x equals x over x plus 2. So in this example, everywhere I see an x, I'm going to plug in 1/2. Substituting 1/2 in for x gives us 1/2 divided by the sum 1/2 plus 2. This is a complex fraction, and we can simplify this complex fraction by multiplying the numerator and the denominator by 2. In the numerator, 1/2 times 2 gives us 1, and 2 times the sum 1/2 plus 2 in the denominator means that we have to multiply the 2 times the 1/2 and the 2 times the 2. So 2 times 1/2 gives us 1, and 2 times 2 gives us 4, which gives us a value of 1/5. This means for this function, function g, when x has a value of 1/2, y has a value of 1/5. That gives us the point 1/2, 1/5 on the graph of g of x. Find f of 8 if f of x is equal to the square root of x minus 7. Again, everywhere we see an x, this time we're going to substitute 8. This gives us f of 8 equals the square root of 8 minus 7. And of course, 8 minus 7 is 1. And the square root of 1 is 1. And this gives us the point 8, 1 on the graph of f of x. In this example, we're asked to evaluate function f when x is equal to 2x minus 1. Now, there's no need to panic. We're still going to follow the same process that we've been following. Everywhere I see an x in the function f of x, we're just going to substitute 2x minus 1 and then simplify as much as we can. That would give us f of 2x minus 1 is equal to 2x minus 1 squared plus 2x minus 1 minus 3. And notice all I've done is substitute 2x minus 1 in for x. When we square 2x minus 1, we get 4x squared minus 4x plus 1. And that's a result of foiling 2x minus 1 times 2x minus 1, because that is 2x minus 1 squared. Now I'm going to bring down my plus 2x minus 1 in the middle. And now I'll bring down the minus 3 at the end. And now we'll combine any like terms that we have. First, we'll combine negative 4x and plus 2x to get a minus 2x. And then I also notice that plus 1 and minus 1 add out. And this leaves me with only the minus 3 at the end to bring down. So when we evaluate function f at 2x minus 1, we get 4x squared minus 2x minus 3. In this example, we're given f of x equals 3x plus 2 divided by x plus 4. And we're asked to evaluate function f when x is equal to 1 over x. So everywhere we see x in function f, we're going to replace x with 1 over x and then simplify as much as possible. This gives us 3 times 1 over x plus 2 in the numerator and 1 over x plus 4 in the denominator. Let's simplify the numerator just a little bit. If we multiply 3 times 1 over x in the numerator, we get 3 over x. So that gives us 3 over x plus 2 in the numerator. And in the denominator, we have 1 over x plus 4. This is a complex fraction, and we have to simplify it. We can simplify it by multiplying the numerator and the denominator by x. When we multiply the numerator by x, we have to multiply the 3 over x by x and the 2 by x. And same thing in the denominator. The denominator is also a binomial, which means we have to multiply both terms in that binomial by x, which means we have to multiply 1 over x times x and 4 times x. When we multiply 3 over x by x in the numerator, the result is 3. The x's cancel out. And then when we multiply x times 2 in the numerator, we get 2x. So when we multiply by x in the numerator, we get 3 plus 2x. And then when we multiply by x in the denominator, we get 1 plus 4x. And because this is a fully simplified fraction, that means that we're done. So evaluating f at 1 over x gives us 3 plus 2x over 1 plus 4x.